Wanna keep you here, cause you dry my tears. Yeah, summer, loving and fight.
So, what is a power series? So, a power series with center C, so centered at some point C, is the infinite series. The following. It looks like this. So here's our power series. That's the notation for it. Equals, and here's our infinite series. Okay. One moment. Okay, so here's our infinite series of some sequence times x minus c, and remember again, c is our center, to the n power. So this is equal to a 0 plus a 1 times x minus c to the 1 power plus a 2 times x minus c to the 2 plus a 3 times x minus c to the 3rd, and so on, dot, dot, dot. So, in this series here, then x is our variable, so x is a variable, and again, c is our center. That's the center around which this is centered, I guess. And also other properties of the power series is that for all x minus c, absolute value, when that is less than a certain r, and this is our radius, then it is said to converge. This will converge absolutely. This series will converge when x minus c is less than a certain value. And we'll be dealing with this this concept in the problems that we'll be completing. And then for conversely, if it is greater than this radius, then it will diverge. Okay, so that's an important quality of the x minus c. And remember, that's absolute value. Okay, and then so this r, another term for that is radius of convergence, right? So radius of convergence. And then if you kind of combine these, so x minus c being, well, okay, yeah. So if we have like x minus c, we know that when it has to be less than r, the absolute value of it is less than r, okay? So what that means is that when we do absolute value, remember, well, I remember in a while back, when I was taking Algebra 2, as far as inequalities, when you have a less than sign, my teacher would always say less than, so that implies like and this. So it is, this value is greater than the negative of whatever your the number on the other side is, and then less than the positive value. So this is basically what it's saying. And then this, another form for that, if you add c on all sides, it looks like this, right? So then we'll have c plus r, right? And this right here, this is called our, another way to write this, there's a lot of ways to write different things, but basically, this thing here, this interval, is called interval of convergence. Interval of convergence, okay? So these two terms are pretty important, the radius of convergence and the interval of convergence, and they're related in the following way. So here's our interval again. I'll rewrite it. C plus R. So basically here, again, where C is the center, so let's say on a number line, here's C. Here's point C. So this is our center of the series. And then let's say our R is some distance. Okay, so here's R. This is our radius of convergence, right? So if you think about it, the radius will go this direction, or R amount in this direction. So this is C plus R, right? C plus R. And then if you go R amount in this direction, then you're actually subtracting it from C, right? So this is our C minus R, okay? So you see how the radius of convergence works with the center to form our interval of convergence, all right? So from this, we have a theorem, of course, because theorems are very useful. So theorem, and this will just be like a formal I guess, statement of what I was just saying. So when you have this, so this is going to be our power series. So we're going to have same form, an x minus c to the n. So this is a power series. Then the radius of convergence, and I'll abbreviate radius of convergence. That's going to be our r. And then if r is greater than or equal to 0, then f of x, this power series, converges absolutely, I'm going to abbreviate again, when, and as I said before, the absolute value of x minus c is less than r, okay? And on the other hand, and then it diverges, yeah, so that was the first case, and then it diverges when exactly the opposite is true, when the absolute value of x minus c is greater than r. Okay, and then there's another case as well when the radius of convergence, it turns out to be infinity. So then in that case, then I guess you could think of it as it'll converge absolutely. The power series will converge absolutely when x minus c is less than infinity. And that's pretty much always true. So the conclusion here is basically that f of x converges absolutely for all x. Okay, so yeah, that's a pretty useful one. All right, so let's do an example of this. So let's say they give you this power series. So f of x equals the following. Series of this, x to the 2n over 3 to the n. And they ask you, where does this converge? Where does this converge? So essentially, they're just asking you for the interval of convergence, which is upon the interval on which a series converges. So yeah, it's kind of self-explanatory. But okay, so here's our a sub n. That is x to the 2n over 3 to the n. Okay. And here we're actually going to, so in the evaluation of what is r and finding the radius of convergence and the interval of convergence, we're going to be using the ratio test a lot. So that's going to be come into play here. It's going to be really handy. So first of all, let's do the fancy P, rho, it's called, is the limit as n goes to infinity, and we're going to implement the ratio test. So a n sub 1, or a sub n plus 1, sorry. We're going to plug in n plus 1 wherever you see an n. Remember, with parentheses. And then n plus 1 here. Okay. And this will be over our a sub n. So that's just the normal x to the 2n over 3 to the n. All right. And then in the next one, I'll flip up the bottom fraction. And we'll break some stuff apart here. So then we have x to the 2n plus 2, right? Because we're going to distribute this 2 in. So that would be x to the 2n plus 2 would also mean, this is another way to write it. And then we have down here is 3 to the n plus 3. Well, 3 to the n plus 1, which is 3 to the n times 3. Sorry, why did I say plus? Times 3, okay? And then I'll flip up the bottom fraction so it can come to the top here. And then on the bottom we have x to the 2n. And then we have some nice cancellations right there. And then the x to the 2n. So we're left with this, which is, I'll write down here. So rho equals limit as n goes to infinity of, and then we have x to the second over 3. And as you see, we don't even have n's anymore, right? So technically this is going to be a constant, and limit as n goes to infinity is just going to be this constant. So x squared over 3. Okay, so now what we can do with this is rho equals absolute value of x squared over 3. And we know by the ratio test that this sequence will converge when rho is less than 1. Okay? I'm going back to the ratio test. So this will converge when rho is less than 1. So now we have this inequality to solve for x, right? So then, what we're going to do is just solve this. So then let's multiply by 3 on each side. So we get x squared is less than 3. Okay, and then we get that the absolute value of x is less than radical 3. Okay, so technically, this is our radius of convergence, right? So our radius, rad of convergence equals radical 3, okay? And then since we don't have a c here, you know how the form, well, okay, I'll continue writing on the next slide so I have some more room. So this is what we have. This is what we ended up with, this here. And this is our r, okay? So that's our r. That's our radius of convergence. And also, as you see here, x minus c, our c is 0. So our center is 0. Center equals 0. So our interval is going to be c minus r to c plus r, which in this case is 0 minus radical 3 and 0 plus radical 3, okay? So in this case, our interval is just going to be negative radical 3 to positive radical 3, okay? And this is centered around 0. All right, so this is our interval of convergence. I'll point that out, interval of convergence. So we technically answered the question, sort of, but this is only a partial answer because now after you find the interval, you do have to check. See here how we have rounded brackets. So rounded means that's open, right? We don't really know what's going on at these exact points, but that's what we're going to do. That's the last step, is to check the power series, like what is it doing at these endpoints. So let's plug in the negative radical 3 and see what we get first. So if we do this, then we plug it into the power series here. So then we'll have, we're plugging this in for x. So in the x spot, now we have negative radical 3 to the 2n over, and then we just have 3 to the n down here. And this turns into a, well, when you square the negative radical 3, it just turns into positive 3, right? So now we have 0, and then this is just 3 to the n over 3 to the n, which is just 1. But then when you have your series, you're just going to keep adding whatever you get when you plug in n. So you get 1 plus 1 plus 1 plus 1 plus infinitely many ones. So this is going to diverge because you just keep adding the same number. So that diverges. So the rounded bracket here is fine. And now let's try the other one. Then we have f of positive radical 3, which when we plug that in, I'll do that real quick. Okay, we plug that in for x, and then we have our 3 to the n. So this is actually going to turn out the same because we have the squared here. So it squares both the negative and the positive. So we're just going to get 3n over 3 to the n or over 3 to the n, which is going to do the same thing. Oh, that is supposed to be a 1. I got carried away with the pluses there. Okay, and this is going to diverge as well. So both are rounded brackets. Yeah, so this is basically our answer. We did have to check the endpoints though, because sometimes it will converge at one endpoint and not another, or sometimes it converges at both even. And in that case, then you'll have the square brackets, like looking like this, the closed ones. Okay?